So nodal analysis is really based on Kirchhoff current law. When we did Kirchhoff current law, or Kirchhoff current law, we dealt with one node. Now you have more than one node. Now let's see how many nodes do we have here. Here's one node. I'll call it node 1, N1. And here's another node, node 2. And the bottom one is the ground. I'm going to ignore that. So the ground, we don't have to worry about it. That's really your ground here. So we have three nodes, node 1, node 2. What nodal analysis said, what you want to do with these problems, assign current any direction that you want. You choose. So through the 2 ohm resistor, which way you want to make the current go? Up or down?
Up, down.
You want? We got up and we got down. So I'll go down. Let's call it I1. Through this one, which way? I'm going to make it go in, no reason. I2. Through this one, which way you want it? Down, okay. I3. So it really doesn't matter which direction. If the value comes out negative at the end, that means your direction is wrong. Everything else is correct. It just should be going the opposite direction. And what you want to do now is you want to apply Kirchhoff current law at each node. So KCL at node 1. Kirchhoff said what? If you take all the current, the sum of all the current going into that node should equal the sum of all the current leaving that node. And what is going to that node? What do you see going to it? I'm talking about node N1.
I2 and 3.1.
Perfect. 3.1 plus I sub 2. And what is leaving that node? I sub 1. Here's one equation. That's equation number 1. Doesn't look like a 1. Equation 1. Huh. I don't know why.
How did you determine which direction I3 is going? Because it's the opposite.
No, I just made I assume. I just pick a direction.
For
Arbitrary. You can pick any direction you want to.
For each one?
Each one of them, yep.
Okay.
You don't even think about it.
Okay.
And really, you just any direction that you want.
Okay.
Now, KCL at N2. Again, all the current going into that node equals add all the current leaving that node. And here, what's going to that node? Node 2.
Did you say 1?
Try again. Oh, well, I'm having us leaving, so I'll just leave it.
Okay.
So nothing really going in. But you're right. I can reverse the direction and make it 1 going in. You're right.
Okay.
But the fact is coming out, I'll just go, well, this is leaving, that's leaving. So the minus 1 is leaving, which would make it a 1 here. So that's why I said you're right. You know? Plus this current, which is what? I sub 2. What else? I sub 3. So you end up with 1 equals I sub 2 plus I sub 3. Notice that's another equation. And this is the first equation. The problem with these equations is what? You have 2 equations, how many unknowns?
2.
Try again. 3 unknowns.
Oh, yeah.
So we can't solve 2 equations by 3 unknowns. Let me write them on the next page so I don't have to keep going back and forth. So these are the 3 equations. If I rewrite this equation, it will look what? 3.1 equals what? I sub 1 minus I sub 2, right? And if I write this one, it says 1 equals what? I sub 2 plus I sub 3. That's not good. 2 equations by 3 unknowns. I'm looking for a number for an answer. It's not going to happen. If I solve them right now, they'll be in terms of one of them. So maybe what I need to do is rewrite all these currents in terms of voltages. And that's always the case for nodal analysis. You want to take each current and write it in terms of the voltage. So I sub 1, Ohm's law, I sub 1 is V over R, right? But which way is it going? It's going down. So does anyone know what the voltage at node 1 is? Does anyone know what that voltage is? No. So let's call it what? V1. And what's the voltage at node 2? V2. So if I label them V1, V2, I sub 1, since it's coming down, notice it's coming down, it's this voltage minus that voltage. The top voltage is what? V1 minus the bottom voltage is what? 0 divided by 2. So it's V1 over 2. I sub 2, which way we define it going? To the left. Remember, when we say the current going to the left, that means the right side has higher voltage than the left side, just like water. It goes from high to low. So that would be, what is then I sub 2 is going to be? In terms of the voltage. Which V? V2 minus V1. The difference between them. And I can't simplify it. And what is I sub 3? I define I sub 3 as going down. So it's the top voltage minus the bottom one. What's the top? V2, the bottom is what? 0 over 1. The math ends up being V2 here. So now what I'm going to do is come back to these equations and replace each current by the voltages, and you should have now 2 equations by 2 unknowns. So here's the first equation, 3.1 equals, I can move this one out. What is I sub 1? V1 over 2 minus, what's I sub 2? V2 minus V1 over 5. I don't like fractions, so I'll jump on my LCD, which is what? Is it 10? So if you multiply the entire equation by 10, you get 31 equals what? 5V1 minus what? 2 times V2 minus V1. 31 equals what? 5V1 minus 2V2 plus 2V1, simplified, 7V1 minus 2V2. Now let's take the second equation. 1 equals I sub 2, which is what? V2 minus V1 over 5 plus I sub 3, which is what? V2. My LCD here is what? 5. 5 times 1, 5 equals V2 minus V1 plus 5V2. So 5 equals negative V1 plus what? 6V2. And now you have how many equations by how many unknowns? 2 equations by 2 unknowns. I should be able to solve them using any of the techniques that we learned in earlier algebra classes. So let me write the 2 equations now down. The other one, 5, equals negative V1 plus 6v2. Now me, I'm looking at it. I'm probably seeing the best way to solve this is what? The elimination method. If you multiply this equation by 7 and leave the top one alone, you will have what? 31 equals 7v1 minus 2v2. The bottom one, 7 times 5, which is what? 35 equals what? Negative 7v1 plus 7 times 6, 42v2. And when you add them, that's why it's called the elimination method, gone. So what do we have? 66 equals what? 40v2. v2 equals 66 over 42. Which will be what? I can just use my...
40.
Over 40. Yeah, thank you, not 42. So 66 divided by 40, 1.65. That's V2. If you know V2, can you find V1? Grab either equation. 31 equals 7V1 minus 2 times V2, and V2 is 1.65. That's 3.3. Bring it to this side, that becomes what? Is it 34.3? What's V1 equal to? $4.9. So we found the voltage at the top for 1 and 2. If you want to find the current, notice we have it too. Right here. We know every single current going through them. You want to find I sub 1? It's V1 over 2. We know what V1, 4.9 divided by 2, 2.45. You want to find I sub 2? It's right here, V2 minus V1. What's V2? 1.65 minus 4.9 divided by 5. And notice we were wrong on this direction. Should be going backward. 1.65 minus 4.9 divided by 5, negative 0.65. And the last one is I sub 3, which is V2, right? 1.65 amps. So we found every single thing about that circuit. If you look at it, we know the voltage here. We know the voltage here. I know this current, I know that current, I know this current. I can tell you the power, everything about it. And notice this current came on negative, which means the direction is not really going in, it's going to be coming out. Because it's negative. And if you take 2.45 and add to it 1.65, does that equal 3.1? Better be. This is 1 going in, this is which one? This is 0.65 going in, 1 going in, that's 1.65. Does that equal this current, which is 1.65? Yep. So KCL is true for all of them. And that's how we handle nodal analysis. As you write 2 or 3 nodal equations, you're going to start by writing them in terms of I1, I sub 2, then you're going to replace the I's with V's because you're going to have too many unknowns for the number of equations that you have. Let me try another one. I'll make this a little bit ugly intentionally. Let me change that black marker I'm using. I got some negative currents going in. See, this circuit has negative 8 amp going up, and it has negative 25 amps going up. It has negative 3 amps going in. Guess what I'm going to do? Because I don't like negative numbers. I'm going to change the direction, make them positive. Make life easy on me. So let me draw that. That's now 8 amps coming down. Leave a space on the top because there's one more source. That's 3. I have a current source here. And the value of that 3 amps. I changed the direction of it already. Well, I should lower it just a hair because I'm going to be another wire sticking out. Let me lower this just a little bit. It's a bigger circuit, so try and squeeze it there. Come on, here we go. Let me lower that a little bit. One. That's 7. There's a current source pointing down. Oh, actually, we changed the direction of that because that's a negative value. So it's going up. They have it pointing down with a negative number. I'm changing it to a positive pointing upward of 25. Five ohms. We have one more resistor to add, and that's right here. It's going to jump over this wire, so it's not attached to this, and is attached right here. And the value of that is 4. Now let's look at that and tell me how many nodes that you see there, not counting the ground. So there's my ground. How many nodes that you see there?
4.
4 or 3?
4.
I got 4 and I got 3. This is 1, right? Let's call the voltage is unknown to us. It's called V1. This one here, another node, V2.
What about one that 3 is?
Wires, there's only wires. That's all one node. Some of you are looking at this different than that. A wire, because there's no element here. A node is a point that will connect 2 or more elements. So this is not different than that. There's no element between them. I could have took this wire and went diagonal to that point. And that would definitely made it 3. So this is really one node here.
What about where that V? Why wouldn't you grab
Where is what?
the 3 amp, the 3 resistor, and the V2?
Where do you look here?
Yeah.
Well, that's the same as this.
Yeah.
That's only a wire.
That's what I meant.
So this is like this. Is that what you meant? Yeah.
Yeah, that's what I meant.
That's the same
I
node.
was
Yep.
wondering why.
Yep. Yep. That's the same node. Now remember, I said I'm going to assign current going any direction I want to. Depends what mode I'm in. So going through the 3, which way? Left or right?
Clockwise.
Left or right, make it easy. Well, I said 1. This is a straight line. I don't know what clockwise for a straight line is. 4, through the 4. Not even going to think about them. Through this. through this. I'm assigning current through each resistor. Oh, I forgot the 1 ohm, right? So we'll call this, let me call it up potentially. I sub 5. One, two, three, 4, and 5. Looks like an S, but that's a 5. I have 3 nodes. I gotta write 3 equations. KCL at V1. Again, algebraic sum of all the current entering that node is equal the sum of all the current coming out of that node. Okay, what is going to that node? Look closely. What do you see going to it? I2 is the only thing I see going to it. What is coming out of that node?
I1 and 8 amps.
What else?
8 amps.
And the 8 amps.
There's 3.
The 3 here and the 8 here and this one. So if I clean that, what's 3 plus 8? 11. Negative I sub 1 plus I sub 2. That's the first equation.
So you always want your constants by themselves?
Well, I like to make them an equation which you put the constant. It looks horrible, the word equation. Like, I don't know why. It looks fine here. So that's equation 1. Now let's do KCL at what? V2. The current in equals the current out. What is going to that node? We're talking about node 2. I1 plus I5. What else going to it?
3 amps.
The 3 amps. Anything else? This, and that. And what's leaving that node? Okay, if I clean it, I can move the 3 there, make it a negative 3. I sub 1 minus I sub 3 plus I sub 5. Equation 2. Nothing. Let's do one more. KCL where? At node 3. Again, the current in equals the current out. And going to that node, going to it, I see the I3, I see the 25. Can you see the 25 on the bottom?
Oh, yeah.
What's leaving?
I4.
And I2. This and this leaving. So if you clean it, you move the I sub 3 there, you get I sub 2 minus I sub 3 plus I sub 4 equals what? 25. Equation 3. Okay. So I got my three equations. Well, in the three equations, I have 5 unknowns, if you can see them. 1, 2, 3, 4, 5. I sub 1, I sub 2, I sub 3, I sub 4, I sub 5. We can't solve them. So I need to rewrite each current in terms of what? The voltage. So let's take a peek here at each one of them. I'll use a red color for that. I sub 1, I have it go in this direction. So I sub 1 is this current, so it's this voltage minus that voltage. What is this voltage? And what's that voltage? V1 minus V2 divided by what? By 3. The resistor is 3. While I'm at it, I sub 2. I sub 2 is the current going this way. So it's this voltage minus that voltage. What's this voltage? 3 minus what? V1 over 4. I sub 3 is the current going this direction.
V2 minus V3.
Good. V2 minus V3 over what? 7. I get 2 more. I sub 4 and I sub 5. Where's I sub 4? I lost it. Oh, right here. So it's this voltage minus this. V3 minus nothing, right? Over 5, which is V3 over 5. And I sub 5, I define it going in intentionally. So it's this voltage on the bottom minus the top. What's the voltage on the bottom? 0 minus what? V2 over 1, which is what? Negative V2. So now I'm going to go back to my 3 equations that we had early and do what with them? Rewrite them in terms of the voltages. Here we go. Let's take the first equation. That's this one. 11 equals negative I1 plus I sub 2. So let me take that equation. And let me replace I sub 1 with what? V1 minus V2 over 3. Replace I sub 2 with what? V3 minus V1 over 4. Equals what? 11. Clean it a little bit there. What's my LCD? Is that 12? So you'll have negative 4 times V1 minus V2 plus 3 times what? V3 minus V1. And what is 12 times 11? Is that 123? 132. Now let's clean it. Negative 4 V1. Oh, plus 3, that makes it negative 1, right? There's negative 4 on this side, plus 3 on that side. Actually, that's a minus 3. You know what? It might be better just do it slowly there. What's negative 4 minus 3? Negative 7 V1 plus 4 V2 plus 3 V3 equals 132. Now let's take equation 2. That's this one. I sub 1 minus I sub 3 plus I sub 5 equals negative 3. And replace everything. So that's one of them. That's the second one. Let's replace each current by the value of the voltage, V1 minus V2 over 3. I sub 3, where's I sub 3? V2 minus V3 over 7. Plus I sub 5, where's I sub 5? Negative V2. And that's equal to what? Negative 3. And again, my LCD for this will be, it looks like 21. If you multiply that by 21, you will have 7 times V1 minus V2 minus 3 times V2 minus V3 minus 21 V2 equals negative what, 63? Clean it. Hopefully I'm going to try to do it in one shot. 7V1 negative 7V2 negative 3V2, that's negative 10, negative 21, is it negative 31V2? And what about the V3? Is that plus 3V3? So if I clean this correctly, this is what I have. Notice quickly, if you add the two equations here, you eliminate V1. And the third equation. The third equation is what? I sub 2 minus I sub 3 plus I sub 4 equals 25. I sub 2 is, what is it? V2 minus V3 over 7. I sub 3, oh, that was I sub 3, right? That was actually I sub 3. That's the negative. Plus I sub 2. I wrote this one first. I got to write this one second. I was looking at the wrong one. I sub 2 is what? V3 minus V1 over 4. So this is I sub 2 and this is I sub 3. I just wrote them backward. Plus I sub 4, which is what? V3 over 5. LCD is not going to be a pretty one here. 5 times 4 is 20 times 7. Is that 140?
Yep.
Oh, that would be negative 20. V2 minus V3. Plus 35. V3 minus V1. Plus 28 V3 equals, is that 3,500? 25 times 140. Oh, I forgot to turn it on here. 25 times 140, I think it's 3,500. 3,500. So let's collect like terms. 35 V1. How about V2? Looks like negative 20, right?
Negative 35 V1.
Negative, yes, thank you, Jordan. Yep.
I think no, it's positive, right? Negative 20.
35 times negative. right?
Oh, no, I was looking at V3. I'm stupid.
Yeah.
Okay.
So let's get to V3 now. This is what? 20, positive 20, positive 35. What's 20 and 35? 55 plus 28. Is that 83?
Yeah.
We can use a calculator. That's 55, 75, 83. Yep. And that's my third equation. So now we're going to solve them. I'm going to cheat. I have a TI-86 here, that 89 has it too, but the 86 is easier for solving equations. Simultaneous equation, they ask me how many equations do I have? I go 3. And I put the values for them. Negative 7, 4, 3, 132. Next one. 7, negative 31, 3, negative 63. And the last one, negative 35, negative 20, 83, and 3,500. And I just hit solve. And there's every one of them. Yep. So I got, here's what I got. If I push the right button, V1 equals 5.42 volts. V2 equals 7.74. And V3 equals 46.32 volts. You can use MATLAB, which I just showed my class, how to use MATLAB to solve 3 by 3, 10 by 10 in less than 30 seconds. You can use Mathematica. You can use a TI-89 has you can download that simultaneous if it doesn't come with it.
You can also do it in the matrix on the GIA.
Yep, you're right. So if you took linear algebra in a determinate matrix, do the inverse of A. Like A is the coefficient. If you really want to, if you know matrices, I'll give you the answer to matrices. If you look at the 3 equations for those people, if I label this matrix A, so that's A, it's the coefficient, which is negative 7, 4, and 3. B is 7, negative 31, and 3. And C is negative 35, negative 20, and 83. Matrix B is going to be the answers. The answers are what? 132, negative 63, and 3,500. Notice if you take this matrix, multiply it by x1 or v1, v2, and v3. So it's really A times V equals B. That's what you have. So you want to solve for V, which is v1, v2, v3. V actually equals v1, v2, and v3. So to get rid of the A, you have to multiply this side by the inverse of A. So you'll find that V equals the inverse of A times B. And I don't know how you do the inverse on the TI if you have a matrix. Is that built in?
You can just plug in the augmented matrix and then reduce it to
To 1,
form.
to 1, 0, 0, 1, 0, unity, 1, 0, 0, 1,
Yeah, that's what I did.
0, 1, 0, 0, 0, 1. Yep, you can do that. The other option is actually, that's true, the other option, what you can do is write your matrix, which is negative 7, I think that's called Kramer's rule, is it? I used to love linear algebra and all that stuff. And you write 132, negative 63, and 3,500. And your goal is to take this and change it to 1, 0, 0, 0, 1, 0, 0, 0, 1, and 3 numbers here. If you did that, if these are the correct answers, you will have 5.45 here, you will have 7.74 here, and you will have 46.32 here.
This is literally what we're doing in data structures right
Is
now.
it?
We have to make a program that finds the inverse,
Yep,
which is hard.
yep. But that's where the stuff comes in handy, you know.
Do you want to tell us how to just
Yep, you go on MATLAB and just says find the inverse. Just write inverse of A.
Just show that so that.
Actually, if you write inverse of A, it does that. Are you doing it in Java?
Yeah.
That's good. So yeah, when people say like, why we have to learn this stuff, that's really a reason why this stuff is important too. Especially, you could end up with 6, 7 equation by 6, 7 unknowns. I mean, with a calculator like this, or the TI-89, you have actually one of those apps on it that will do simultaneous equations. And if it's not on it, you can download it, you know. By the way, sometimes, this is the circuit we just did. A lot of times when they draw the circuit, they don't draw it like this. In the lab, remember, when you connect things, it's not always 90 degree. It's wires hanging like these. So it looks different, but it's not. But when you do it like this, oh, that's node 1, that's node 2, that's node 3. So sometimes when we graph them, like we make them look straight line, perfect, and everything. Yeah, good luck. In the lab, they all look like wires just floating around. Notice they do it. Here's the inverse. Is take the inverse of that determinant minus this one. That will give you the answer. They're actually using MATLAB for this. Use MATLAB. What about if you have a dependent source? Does that change anything? No? Yep. Let's talk about determine. Let's put a dependent source there. Actually, Supernode makes it really easy. But I don't think I'll get a chance to see it today. So let's take this circuit where we have a dependent source. I'm going to use a blue marker because the black one is dying. 15 amps. That's another example now, different one. This is 1. This is 3. And this is defined as 3Vx. And Vx is defined as plus to minus right here. Ooh. This is 2. That's my circuit. And again, I'm going to find everything about the circuit. I'm going to find all the voltages, the currents, and everything. Through every single element. Okay. Let's look at this. How many nodes do you see there?
on top?
There's one on the top. We'll call that voltage V1. You get this one, V2. That's your ground.
Between 2 and 3. No.
That's actually going up there too. That's the same node. Remember, there's a wire connecting this, right? That's all the same node. If there's no element between them, still the same node. So that's your ground. All of that is your ground. And if you don't believe it, you could have drawn this like this. And this one here is really attached to this end, so if you want, you can attach it like this. And where's that one on the top? That's the one here. And this one, it's attached right here. That's what that circuit looks like. This is V1. This is V2. And this is your ground. It just looks different. So that's good. If you have V1, V2, there's a good news. Why? How many equations by how many unknowns you're going to have?
2 equations.
2. If you get 3 nodes, V1, V2, V3, guess how many equations you're going to have? 3. If you get V1, V2, V3, V4, you have 4 equations. So you know before you get to it how many equations by how many unknowns. So let's assign current, again, any direction that you want to. This is I sub 1. I'll do it this way, I sub 2. I sub 3. I should have went 1, 2, and 3, label them with the resistor, but I don't know.
Yeah, but we have 20.
I wasn't even thinking. So KCL, add V1. What is going there? 15. What's leaving? And 3. The current in equals the current out. KCL at V2. What do we have going in? I sub 1 plus 3Vx. And what's leaving? I sub 2. 2 equations by how many unknowns? 4. I1, I2, I3, and Vx. 2 equations by 4 unknowns. Not good. Let's write them in terms of voltages. What is I sub 1? Let's look at this. It's defined coming down. So what is it?
V1.
V1 minus V2 divided by 1, which is V1 minus V2. Good. I sub 2. That's this current.
V2 minus 0.
V2 minus nothing over 3. V2 over 3. I sub 3. That's this current. V1 minus nothing over 2. And what about Vx?
0 minus V2.
Well, almost. It's backward. Notice where the plus is. The plus was labeled here, the minus there.
Yeah, no.
So it's this voltage minus that voltage. Not divided by, just the difference between them. Because it's a voltage. Vx is a voltage. So it's this voltage minus that voltage. It's the difference between this end and that end.
Which goes into the ground, so it's 0.
Yep. So now just fill in the blanks here. Replace each one. So here we go, 15. No, I'll come back here. What's I sub 1? V1 minus V2 plus I sub 3, which is what? V1 over 2. You multiply by 2, you have what? 30 equals 3V1 minus what? 2V2. If you clean it, that's what you're going to have. The second equation, I sub 1, which is what? V1 minus V2 plus 3 times Vx. Vx is what? V2 equals I sub 2, which is V2 over 3. Multiply by 3. 3V1 negative 3V2 plus 9. Negative 3 plus 9 is what? Plus 6 minus the 1 plus 5V2 equals 0. Three V1 minus 3V2 plus 9V2 plus equals V2. So 2 equations by 2 unknowns. I can go to my calculator quickly here while I'm on this page. I go simultaneous. Tell them it's 2 equations by 2 unknowns. And the first one, 3, negative 2, 30. The next one, 3, 5, and 0. Solve. V1 equals 7.14 volts. And V2 equals negative 4.29 volts. If we know V1, V2, can we find I1, I sub 2, I sub 3, and Vx? We got them all. So that's introduction to nodal analysis. It's really nothing more than KCL at more than one node, 3, 4 nodes. Now, what's going to happen next class, we're going to have something called super node, and that is when you have a voltage source in the circuit, you know, because if you had a voltage source, I'll just give you a heads up on it. If you have a circuit that looks something, don't write this one because that's just quick thinking about next week. And let's say you want to do KCL of this node. You go the current going in. Well, there's a current going in. There's this current going in. What's the current through this? How are we going to find what that current is? None of us will be able to figure that current. So that's where we're going with the super node. What does that mean? Which is actually good for us, because if this is ground, you know what the, let's say this is 5 volts. You know what the voltage here is? Which is what? 5. So how many nodes left in that circuit that you don't know the voltage to? Only one. That's this one. So having voltage source is a great thing when we're doing nodal analysis, because once you know the voltage of that node, there goes one equation out. The number of equations is going to be equal to the number of nodes that the voltage is unknown there. So the only one in this case, you don't know the voltage is this one. So you should only have one equation by one unknown. We'll wait till next class on this. So, but that's where we're going with the super node.